Welcome to solverfy.
This is problem 15 of chapter 27, looking at the 4+2 cycloaddition of this given reaction. Since this is a 4+2 cycloaddition, we know it will involve the 4 pi electrons of our diene, which we see here, and the 2 pi electrons of a dienophile, and we'll use one of the double bonds on the benzoquinone. And it's a thermal 4+2 cycloaddition since it's run under heat, as indicated here, which means it is a Diels-Alder reaction. Our diene is shown here in the S-trans conformation. S refers to this single bond, and we can see the double bonds are trans to each other across the single bond. But for a Diels-Alder reaction, the diene must be in the S-cis conformation because an S-trans diene would lead to a cyclohexene with a trans double bond, which is impossible to form. So let's redraw our diene in the S-cis conformation. And now we can draw our mechanism arrows to see what our product will look like for the answer to part A of this problem. And if we follow our arrows, then we can draw our product. And we see we formed a new 6-membered ring, which is what we expect from a 4+2 cycloaddition. By forming this ring, we've also formed 3 new stereocenters, which I'll indicate here, here, and here. Part A also asks to indicate the stereochemistry at these new stereocenters, and to determine that, let's move on and look at Part B. Part B asks us to draw the p orbitals of the bonds we used in this reaction, so let's draw this a little differently to try to visualize how the new bonds are being formed. So here's our dienophile. And here is our diene. So we can imagine that the diene is being introduced from below the dienophile. And now let's draw the p orbitals on this diagram. Here are the p orbitals for the dienophile and the p orbitals on the diene. A thermal cycloaddition happens between the ground state HOMO of one of the reactants and the ground state LUMO of the other reactant. Let's draw in the ground state LUMO orbitals of the dienophile. And the ground state HOMO orbitals of the diene. We could also consider the LUMO of the diene and the HOMO of the dienophile. You could try that for yourself to see the result would be the same. So we can see the lobes of the diene and the dienophile match up perfectly, allowing the 2 new bonds to be formed. Since we are imagining the diene to come in from below, we can imagine that the hydrogens on the dienophile are being pushed up and out of the way. And similarly, the ester on the diene is being pushed down and out of the way of the newly forming bonds. So we can now indicate the stereochemistry of our new stereocenters. The 2 hydrogens were both pushed in the same direction, so they are cis to each other. And we said they were being pointed up or pushed up, so let's show them pointing up on our product. And we said the ester was being pushed down, so let's show it pointing down on our product. Now, we could also consider the diene to be introduced from above the dienophile, in which case we would draw the hydrogens pointing down and the ester pointing up. This would give us the same relative stereochemistry, and in this case it would be the enantiomer of the product type drawn here. You can prove this to yourself by building a model of the two products. This completes problem 15 of chapter 27. For part A, we drew the product of the 4+2 cycloaddition and indicated the new stereochemistry. And for part B, we drew the p orbitals and explained how the orbital overlap led to the new stereochemistry.